Union has agreed to undertake major cuts in greenhouse gas emissions and to increase power generation from renewable energy sources.
Good as anything.
Wind power will make up much of Europe's future power generation. Several major projects are already being constructed and planned on the continent, in the North Sea, and along the UK coastline. Wind power can only be generated when the wind is blowing, and variations are considerable over time. These variations do not always correspond with the consumption. A large share of wind power would represent a major challenge to the stability of the transmission systems and the security of supply for the consumers.
So I guess this is not a public message, but a partisan message from a company that owns dams in Norway, as you'll see.
There is a need for backup capacity in order to generate power on days with no wind and high demand. There is also a need for storage capacity for surplus power on days with strong wind and low demand. In Norway, with its long history of hydropower generation, we find half of Europe's reservoir capacity. New pumped storage power plants in connection with existing reservoirs could be part of the solution in securing a reliable energy system. On windy days, surplus power could be used to pump water from low to high altitude reservoirs. This water could in turn be released to generate power on days when demand is high and wind levels are low. This cycle can be repeated over and over again. In order to use Norwegian hydropower reservoirs as rechargeable batteries for the European power supply, more transmission capacity must be established between Norway and the major European consumption areas. Pumped storage power solutions must be developed in such a way that the environmental impacts are reduced to a minimum. The climate threat is a global challenge. A further development of Norwegian hydropower can contribute to a more reliable and, not least, a cleaner European energy supply.
So pumped storage, I guess we talked about it before. So one idea of being able to level the grid when you have lots of renewables in it and you need to have power when the sky is dark at night and when the wind's not blowing, and use up excess which you can't use up in the grid. And so pumped storage is one way to do it. I guess there's also one in Pennsylvania, right? Must be images. It's on the Allegheny, so somewhere in northern Pennsylvania. Seneca pump storage stream. So it's on the Allegheny, which I guess flows into south into Pittsburgh and along the northern tier of Pennsylvania. And so all it is looks like a man-made lagoon up top, a dam on the Allegheny, and pumping up to be able to use it. So obviously there's a pipe that's inside the mountain that transmits it, and so we know from head losses in pipes that it's not a perfect machine. You don't have zero losses on the way up and you don't have zero losses on the way down. You have roughly the same losses if you're traveling at the same velocities, and so they become subtractive from the power, so you don't get something for nothing. But you can reduce those losses, I suppose. We know that the losses are proportional to v squared, and so you'd like the velocity to be as small as possible, and you can do that by having a large diameter pipe, which is most efficient in terms of losses, but is most expensive in terms of construction. So it's capital costs versus operating costs, I suppose, that come into play there. And the other place where pipes come into play in a big way is in the subsurface for wells. Wells to get water out of the ground. We sit on land where we have a 300-foot well that probably a 6-inch bore that brings up water. Has a submersible pump at the bottom which just pushes up. You can't suck up 300 feet because we know that if you put water in tension more than 30 feet, it will cavitate. So you have to push it up. And the same for hydrocarbons. So Pennsylvania, natural gas and tight oil and conventional oil at one stage. The shale gas requires that the formations are so low permeability, which means that the pore throats are very small. We talked about an equation that describes the permeability as a function of the diameter of the pore throat squared. And so if you have something that's 10 to the minus 18 meter squared permeability, it means the pore throats are something like 10 to the minus 9 meters in diameter, which would be a thousandth of a millimeter, very small, lots of them. And so to make permeability high, you have to create permeable pathways. So that's what hydraulic fracturing is all about. You create artificial pathways which have large openings. We know that the transmission is proportional to the opening squared from what we looked at for ducts before. And that allows you to be able to fracture it. So you put down a well, you have a perforation gun, which is just a shape charge that blows through the casing. Then you pump up the pressure to drive these hydraulic fractures. Then you put in sand to be able to fill them, to keep them propped open. And then that sand has some relatively high permeability, which allows the gas to flow back and up the well and into people's homes. So pipe flow, perhaps not the most exciting thing we've ever done in this class. I think we've done some exciting things, but a necessary thing nonetheless. And on my way here this morning, I guess I came past this. Just in the building that's been renovated opposite the creamery. And it's what do they call them? I've forgotten what they call them now. It's cantilevered pipe. It's putting cement into the top small window of this building, which is being renovated, presumably pouring a concrete floor. There's this pumping apparatus with this umbilical is delivering it here. There's a concrete truck that's putting the stuff into a hopper. And so you exactly know how to do this. The hopper is at zero pressure on the top. The bucket or the floor is at zero pressure where it's being delivered. There are different elevations, so you've got the difference in elevation. You have a pump head, HP, which you need to calculate, and you have losses in the pipe, which vary with the velocity at which you pump it. And so that's kind of the essence of the problem that we're trying to deal with. So given that, do we have any questions coming from what we've talked about so far? Hearing none, we'll do the same as before. Go over exactly a little bit about what we've already talked about. I suppose it's perhaps useful to remind ourselves of the problems that we're dealing with. And so we have type 1, 2, or 3 problems. And they vary based on the parameters of geometry, flow rate, or head loss. So geometry for us, I probably started these too low, but is a diameter, a roughness, and a length. Flow rate is either a velocity or a volumetric flow rate, and head loss is HL or delta P, which is equivalent to it. So those are the things that we're trying to solve for. I'm going to I'll move these down. And so I guess the first one we dealt with was type 1. So we're given everything except for head loss. So this is our question. And we're given each of these. And so typically the solution is that we have head loss is equal to friction factor length over hydraulic diameter times v squared over 2g. And so to be able to solve for that, we're given a value of v. So v goes to calculate a Reynolds number, which is just equal to velocity, characteristic dimension, density over viscosity. And we use that then to calculate friction factor. And I'm running out of space. And we use that to calculate a head loss. Pretty straightforwardly. Bless you. So everything's preordained. You know the geometries, you know all the characteristics of the system. You know all the geometric components, and you know velocity. So you have this. So as a function of this, you can calculate from a velocity, diameter, density, and viscosity a friction factor, and then you can use that in here, I guess, to be able to calculate head loss. So that's the easiest one for us to deal with. That's kind of messy. I'm just going to move them down. So we talked about type 2, a bit more challenging. So we want to be able to calculate the flow rate as a function of knowing these other two components. So we have the same conundrum. We can still calculate it from this expression, but we don't really know what the friction factor is to start with, because we don't know velocity. So I suppose we need to have some kind of idea of what the friction factors are. And we got a Moody chart somewhere, I guess a long way back. I guess if we go back here. But we know a couple of things about the Moody charts, if we ever get there. And that is, on the right-hand side, it's a function of friction roughness. Relative roughness is friction factor. And on the left-hand side is a function of Reynolds number. And we have a rough idea of the magnitudes of these. They go from a tenth to a hundredth. So we know a ballpark what these might be to start off with, because we have to guess that if we don't know what the magnitude is. And so for these, for type 2 problems, we're going to have to get the right place again. We're going to have to choose friction factor, and that's going to be somewhere between 0.1 less than and so with a friction factor we can calculate this friction factor. We can calculate for a given head loss. So we have a value of head loss. We can calculate v squared equals HL dH over L (2g) dH over F. And so now, if we've assumed a value for the friction factor, and we know this, and we know the geometry, and we know gravity, we can solve for this, I guess. We can use that to calculate Reynolds number, which is equal to V rho dH over viscosity. And we can use this to recheck friction factor. And go back through it. So if our initial estimate is no good, then our Reynolds number will tell us that we're off, and we go back to the Moody charts to do that. That's what we did last time. And so if you remember, if I go back to this, that's exactly what we did multiple times. We did it up here, right? No, we did it down here. So we get V squared, get Reynolds number, get a friction factor from it, and then keep on repeating it. So that's what we did last time. And so I'm not sure I want to start. I don't want to FaceTime. Let's call someone. And so, why did it keep? Oh, that's why it's this. So this is the sequence. Get an estimate, get a velocity from this equation, get a Reynolds number, check it against friction factor. If it doesn't match up, then just repeat the cycle. And we did that straightforwardly. And so now we're left with perhaps the type 3 problem. So let's go back to what we said before. So type 3 is now the one that we'll do starting now, which is that we want to know what the geometry is, and we know what the volumetric flow rate we want, and we know what the head loss is that we want as well. This is type 3. And so what's the sequence that we need to be able to do that? So let's just do an example straight away. That's the next thing we had up here. So type 3 problem is, we start off with a definition. Just a pipe, don't worry about the tanks on either side. We can just write it in terms of upstream pressure and downstream pressure, or a head loss. So if we describe what the head loss is that we want, we describe what the velocity is that we want. If we have a relative roughness, we don't have a relative roughness. Even if we have a roughness, we don't have a relative roughness because we don't necessarily have a diameter if we haven't dimensioned the system. So we need to make an estimate by taking a value of a diameter. And so we want the pipe to flow at 1 meter a second for a head loss of 1 meter. Let's take a diameter. We don't really know what that should be. But what we can do is we can calculate, first of all, what the Reynolds number might be if we assume a diameter. So if this is in meters, so this is 1 centimeter diameter pipe. So velocity, diameter, density, viscosity, numbers that we've used already. This comes out for 1 meter per second for an assumed velocity, and for a 1 centimeter diameter pipe to be 10 to the 4. If we use, fine, if we use everything. So the velocity is 10 to the 4. If we use that, sorry, not velocity, Reynolds number is 10 to the 4. So if we use that on Moody charts, top one is bigger. See if I can get this right this time. So 10 to the 4, if it's a smooth pipe, is here, 0.03 or 0.0295, 0.03 I think I used. So now with our head loss equation, we have a value for friction factor, which we know. We can substitute that value in here by rearranging for the diameter, which we want to solve for. So we take the head loss equation that we had before. Instead of rearranging it, bless you, for velocity, we rearrange it for diameter. We have this. And so we have friction factor, 1 meter long, head loss of 1 meter, velocity of 1 meter squared, and 2g, so 9.81 times 2 is 20. It comes out to 0.015 meters for diameter. So this is 1.5 centimeters. So now we have to check whether we used the right friction factor. So revise the Reynolds number, put in 0.015, multiply out. We have 1.5 times 10 to the 3. See if I'll use the big one again. So 2 times 10 to the 3, 1 times 10 to the 3. This is 1.5 times 10 to the 3. Is that right? .041 or something. Hopefully that's right. Is that right? This is the revised friction factor. Maybe 1, not sure. Probably don't need to do that. Go back in. Diameter is equal to the friction factor, length, head loss, etc. And you end up with a magnitude of 0.02. If you solve it again, it started off at 0.02. We revised it with the friction factor to be 0.015. It's starting to oscillate between these two, and it'll just jump between these two. And so it's clearly between the diameters of 1.5 centimeters and 2 centimeters. We know that in this regime, it's also turning out to be, it's switching between these numbers. We know that it's laminar, so we know also that we could calculate it by using this value here as equal to, the friction factor is equal to 64 over Reynolds number. And so we could also substitute that into our equation, and that's all I've done on the following line, is that because this is just oscillating back between 0.02, 002 and 0.0015, then the other way to solve it is to write the equation out in terms of friction factor, which includes this term here. So this term here is friction factor, 64 over Reynolds number. If you substitute density, density, velocity, 64, viscosity, length over head loss, velocity squared, and 2g, then you end up with this value out here. So you can always get it as a function of the magnitude, which ends up being halfway between it, right? So this is midway between 1.5 millimeters and 2.0 millimeters. Yeah, so it's 0.03. This is 10 to the 0.001 is 1 millimeter, right? It's not centimeters. So this is the diameter that you need to be able to get that, and that's the solution. Kind of not a very sensible, not 1 millimeter pipes or 2 millimeter pipes are pretty tiny, so perhaps not a very sensible solution. But you can always get it as a function of what we've just done. Okay, so those are the three different solution methods that we can use. And the rest is just to do some examples, maybe. So, coming back to this. So I guess the solution for this is, what we did was we chose a, let me go back to it. We had to choose a diameter to start off. That gave us the Reynolds number. So Reynolds number equals a velocity, diameter, density over viscosity. That gives us a friction factor. Friction factor gives us from, I won't change it around, HL is equal to friction factor length over diameter, V squared over 2G. So of these, we know absolutely everything. Actually, it's probably easier to say the things we don't know. We don't know this. we do know head loss of a meter, length of the pipe, the friction factor, which we've got from the Reynolds number, we've got gravity, and we know the velocity we want to flow at. And so we go back to a new diameter. We calculate a second value for this, a second value for this, and then a second value for this, and we go back and we do a third, etc. Just the same. So those are the sequences. So it's nothing more than that. So maybe we can do some examples. Type 2 and 3 problems are the most complex because we have to be able to guess some things. And so there's some example. I know, I'll leave that up there 2 seconds more. Because these are basically the recipes for getting these solutions. And then using it judiciously. If you look at examples, I won't do that one, but these are just questions out of the book. We did type 1s yesterday, on Monday, so these are types 2 and 3, 2 type 2s and 1 type 3. So you have a system with a tank in it. You're pumping from the tank to downstream. It goes through a pump, which is midway between the upstream and downstream. There are head losses along this pipe. The pump adds 25 kilowatts, which is, in our parlance, what we've called W dot, the work. The flow rate is 0.04 meters cubed per second, so Q equals meters a second. Velocity is equal to Q over A, which is equal to 0.04 meters cubed a second over whatever the diameter is. Diameter is pi d squared 4. And so we have a velocity in the pipe, and we have to write the energy equation between upstream and downstream. The only twist here is that there's a nozzle, which is different from the diameter of the pipe. And so the velocity 2 will not be the velocity in the pipe. So I guess we need to be aware of that. And we write the energy equation between upstream and downstream. So that's all we have here. So the pressure head, the velocity head, and the elevation head upstream. The head of the pump, we only have a power, not a head. We have a downstream pressure, a downstream velocity, and a downstream elevation, and whatever head loss is within the pipe. If we look at the terms that we know that the pressure at 1 is going to be 0. We know that velocity 1 is going to be 0, big tank assumption. The head at elevation 1 is not. If we know that, I guess that elevation head is equal to h. If we take so this would be h. The pressure coming out, if we take it outside the pipe, then this is also equal to 0. The velocity squared is not going to be v, but it's going to be v2, and z2 is going to be 0. So the only terms we're left with is this head, the head loss in the pipe, which is this term here, which is a function of velocity, and a function of velocity 2 for the pipe. So we know what the flow rate is. So since we know what Q is, we can get the velocity as being equal to Q divided by A, because we know the diameter. So that is what this term is here. Q is equal to 0.04 meters cubed a second divided by pi d squared upon 4, which apparently is 31.8 meters squared. We know that the nozzle diameter is not the same as this diameter, so the cross-sectional areas are related to V2 A2 equals VA. And so I guess V2 is equal to V times A over A2, which is going to be equal to V bar D squared over D squared, I think, right? For these two different diameters, which is, or you just do it by directly calculating this, I guess, okay. This is the nozzle diameter. This is 0.04 meters squared. This is the pipe diameter, 0.06 meters. So we have each of those. And so now we have this absolutely defined, this defined. We know what HP is, and so we need to know what H is. So if we assemble those terms, we have the magnitude of V squared over 2G plus friction factor, length over diameter, V bar squared over 2G, and that has to equal this. We don't quite know what this is yet, but we have to write it in terms of power, which we have always chosen to write as this, unit weight and volumetric flow rate. We have HP, power is equal to 25 times 10 to the 3 Newton meters per second, watts. 9.8 times 10 to the 3 newtons per meter cubed, 9.8 kilonewtons per meter cubed, and then the volumetric flow rate is 63.8. If we put 63.8 meters in here, we're left with only one term, which is the value of H, which turns out to be 69.5 meters. And so the head losses are this. So the value of H in driving the flow has to be equal to this. The net head loss in the system, where this is providing some energy in the system. Okay. If you turn off the pump, you can do this just by putting this equal to 0 and solving it again. Now, I guess that what we're solving for is that we know what H is, but we don't know what V2 and V are. And so we need to be able to do that with the pump. We can always relate V2 and V through the ratios of the diameters squared. These are just the cross-sectional areas. And so we can write V2 as a function of V and just substitute it into the equation, where this is going to be, this is 2G, and this is V squared plus friction factor, length over diameter. So this is the correction factor for the velocity through the nozzle as a function of the velocity in the pipe, the velocity in the pipe, and the friction factor, which we're given the length of the pipe over the diameter of the pipe, and the only remaining parameter is V squared, which we can separate out because it's the same term, and we end up with a value of velocity. And if we know the velocity and we know the cross-sectional area, we get a volumetric flow rate. So always well, not simple, but always a twist. I guess the twists in this are that the velocity that we use to calculate the head loss is the velocity within the pipe or the fitting, and the velocity at the end of our flow system is V2, which is the exit velocity, which is related to this, but it isn't the same. If the nozzle was the same diameter as the pipe, then V2 and V bar would be the same, and we would be able to gather them straight away and just have 1 plus F L over D all times V squared over 2G, right? If we did that. So how to deal with a pipe. So we're just using, again, the energy equation written between upstream and downstream. Okay. Type 2, I guess one more type 2. In English units, unfortunately. Same kind of idea. You have a system where you have upstream fluid pressure, downstream fluid pressure, and a pump in the middle. You're pumping from a large, closed, pressurized tank. So large means velocity 0. This is the upstream. You have a friction factor which is given, which is 0.025. 0.025. So I guess you know it's assumed turbulent. So you'd be, if you have our Moody chart, we know that we're somewhere like this. So turbulent part. No minor losses, so it's going around bends, so KL are all equal to 0. Determine the flow rate if the pump adds 1 horsepower. Well, it's going to be in English units, so we'll suffer with that. So we know this is upstream, we know this is downstream, so we have to write the energy equation between upstream and downstream. So this is the upstream portion here. This is the downstream portion here. And these are our head losses in the system. What do we know? Do we know big tank approximation? So 0. Z1, well, it depends where we take our datum. It might be worthwhile taking our datum here. There's no reason we can't do that. I think that's what they do here. So this would be 0, and this would be 8. The pump has 1 horsepower, which is 1 HP. I can't do the conversions, but not pump head, but 1 horsepower. And downstream, pressure 2, 0. V squared over 2G, we don't know. We know the elevation here is going to be 8 feet. We know the elevation. We could choose different datums, but choose a different datum. I guess there is only one datum. And I guess we need to know the pressure. So we know the pressure. We could write Bernoulli between 0.3 and 0.1. If we did that, we know that the velocity here is 0, pressure here is 0, and an elevation. We know that the velocity here is 0, we know an elevation, and we don't know the pressure, so we can solve for the pressure. It's just going to be the static head of water, which is here, which is going to be P1 is going to be equal to 8 times gamma W. Right? It's just this static head of water that has to be there. So this is here. So if we use this, this is a length. So this is 8 feet also. All these are lengths. 8 feet, 0, 0. This is not 1 horsepower, but it's some pump head that we need to convert. Pressure at the nozzle is 0. Velocity of the nozzle we don't know. Elevation of the nozzle we know. And we don't know the velocity in the pipe, but we know, since this case, the nozzle diameter and the pipe diameter are the same, I think, which is equal to this. Then we don't have to worry about relating these two to each other. So here's the calculation. We need to convert the pump head into the known power. This is power, unit weight, volumetric flow rate, 1 horsepower. This must be the conversion. It must be 550 foot-pounds per second. I don't know that. This is the unit weight of water, 62 pounds per cubic foot. Pi d squared upon 4 times the velocity, which we don't know, but it is the velocity. So we have the pump head defined as a function of a number divided by the velocity, where the velocity has to be in units of feet per second, because it's written this way. So the velocity has to be in terms of feet per second, just because the way that we've done it. We also have the first equation here, which we can rearrange for the things we know. So now we know what this is. So this is this term here. There are no other terms on the this side here, because I guess this and this will cross out, just as it works out. And so we're left with only v squared over 2g and v squared over 2g with a friction factor. So v squared over 2g is taken out. The first one here is this. And the second one here is this whole term here for this friction factor. So friction factor is 0.025, 25 feet of pipe, 0.012 feet in diameter. This multiplier on this is just 1 times this instead of this term here. This is 1 plus this. And as a result of this, we have a v and a v squared. So what I guess we have to do is we have to multiply both sides through by v and v. So this becomes v cubed, and then we can, then we can manipulate it and cube root it. And so if we do that, we end up with a value for the velocity coming out of it. If we know the velocity and the area, we can calculate a volumetric flow rate. Comes out of it. And so by including the pump in, we get a volumetric flow rate is this. So then the second part of the question is what happens if we raise this outlet up 2 feet, I think, right? Yeah. So if we raise this up to here, so it's 2 feet higher. Didn't want to do that. Don't know why my pencil has changed into something else. So now it becomes exactly the same question as before, except now this is 2 feet higher. So this would be 10 feet. And I think the only thing looking at this that changes is now that when we look at both sides of this expression, we have 8 feet of head acting inside the tank, which is the pressure head, but we have 10 feet of elevation. And so immediately these two don't cancel out on either side, so you're left with an extra term on the right-hand side. And so they're asking what physically happens if you do that, is you basically end up with an extra term. You have an 8 on one side, and instead of having an 8 on the other, you don't, so they don't cancel out. So you're left with a net term which is equal to 2 plus this term here, right? And so if you have this term here, then when you multiply both sides by velocity, then you end up with multiply this by velocity, so you get rid of this. You multiply 2 by velocity, you get this. And you multiply this by velocity, and you get this. So you get something which is a function of velocity and velocity cubed. So you end up with a cubic equation to solve. So instead of being able to solve it just by taking the square root of or the cube root of the velocity here, after you rearrange for these terms, you need, so v over v gets rid of the v. You only have a v cubed term here. So you can take the cube root of this equation once you've rearranged it, and you can solve it in one go. Here you end up with a cubic equation, which means that you have 3 solutions. 2 roots will be positive, and one is two roots negative and 1 positive, and the positive one is the right one. It's the only correct answer, and so it ends up just being a complex solution. Okay. So those are the type 2 questions. Type 3 is to be able to dimension a flow system, and these are also kind of complex, but we did one with the circular pipe, finding out what its diameter would be. One happens to be for a duct. Same kind of idea. You want to decide the size of it. And a duct is a bit more complicated because in this particular case, they want it to be the same width to height ratio. So you want air to flow through the duct. It's smooth, so that's interesting to know. It's moving at a rate, you want the air to move at a rate of 100 cubic meters a second, but you want the pressure drop to be equal to 44 millimeters of water. So delta P over gamma W equals 0.04, right? So this is water, and this is pressure. And so the pressure drop that's driving it is going to be equal to this. But this is the pressure drop of due to water. And you're going to be blowing air through the system, so you have to be a little careful with that. So if you write Bernoulli between upstream and downstream, as we do, we want to have this pressure drop, which we'll retain, which is the essence of our problem. We know that the upstream and downstream pressures will cancel because the cross-section of the duct isn't changing. And we know that if the duct is horizontal, then these two terms also will cancel. They won't be zero, but they would cancel. And so we're left with P1 minus P2 over gamma air is equal to friction factor length over diameter hydraulic times V squared over 2G. So I guess that's the essence of the problem. This pressure drop is defined in terms of height of water, and this pressure drop is defined in terms of unit weight of air. Velocity you want to get going through is 100 cubic meters a second. We know that the area is going to be a length times a height, I guess B in this particular case. B is equal to 3H. So area is equal to B times H, which is equal to B, which is equal to 3H times H. 3H times H. And I guess we want to know the perimeter, which is going to be equal to, not pressure, uppercase P, perimeter, which is going to be 3H plus H times 2. Perimeter is this length plus this length, and it's 2 times that. So then we can get all the other things you need. Velocity is volumetric flow rate divided by the area, which is equal to 100 over 3h squared, where h is given in meters, which we have to be careful about. And we need to be consistent with our velocities, even though we don't have velocity here. We need to use the hydraulic diameter, which is equal to 4 times area over perimeter. 4 times the area is 4 times 3h squared, which is this term here, divided by the perimeter, which is this term here, which if you multiply it out comes to 1.5 times h. H is in meters and dh is in meters. And the pressure drop we get, which is equal to friction factor length over diameter, a half rho v squared. And the pressure drop we've converted by making sure we use density of water and the height. Height is 40 millimeters, 0.4 meters. This is the unit weight of water, so we can calculate the pressure drop in terms of that, which is 392 newtons per meter squared. So we immediately have this magnitude. So we know that the pressure drop in terms of the correct magnitude is a function of friction factor, length over diameter, density of water density of air, sorry, times V squared. And if we put those terms in, 50 meters long duct, the hydraulic diameter is 1.5 h. The term here is a half. The density of air is 1 kilogram per cubic meter, as we use, or 1.23 in this case. And the V squared term is from this. V squared term would be this. So it's 100 over 3h squared here. And we also, so we know from this, we only have one term here to solve for. So we can rearrange that equation. And I guess if you rearrange this equation, you get f as a function of h squared. It only has h. We know what kilograms per meters are, and we know what meters are. So we end up with that. And so we can get a friction factor in front in terms of h squared. And we also can calculate the Reynolds number, which would be a velocity, a length, a density, and a viscosity. Did we do that already? No, we didn't. And if you do that here, I guess they're using kinematic viscosity is equal to dynamic viscosity divided by density. So that's what this term is. You can see from the form of this equation, it's missing a density and a dynamic viscosity on the bottom. So if you put in the velocity term, which we have as a function of geometry, you have the hydraulic diameter as a function of geometry, and we know what the viscosity of air is. It's roughly 10 to the 5 meters squared Pascal. Well, it's not in Pascal seconds. It's roughly 10 to the minus 5 Pascal seconds. This is what it is as a kinematic viscosity. We end up with the Reynolds number. And so you can use these solutions for the equations we have, which are, where's equation 2 is this, friction factor. Choose an H, get a friction factor. If you know what the friction factor is, you can calculate a velocity, I think. So assume a friction factor. So you get a value of H for that friction factor. We can define Reynolds number as a function of H, so that value of H can go into the Reynolds number. We get a Reynolds number out of it, which we can check. We can check from the Reynolds number whether it's the right friction factor, and if it's not, then we go back and get a new friction factor by using the Reynolds number for a smooth duct. Use that friction factor back again to be able to use the revised friction factor to give a new dimension of the system, which corresponds to a new Reynolds number, which then allows us to get a new friction factor and ultimately to zone in on one that doesn't change as we go through multiple iterations. So not very straightforward, but one that ultimately, as we did for the circular pipe, it oscillated between 1.5 and 2 millimeters, but ultimately zones in on some region, and therefore you have a duct that's defined in terms of both its height, and because its height to width ratio is also defined, then it defines a width as well. So complicated, but perhaps worthwhile walking through. And that was it, I think. I wasn't going to do anything else. Yeah, okay. So we've type 1 problems, definitely the easiest. I did mention that they are the first and the third question are type 1 problems. There are no type 2 or 3 problems that we've done today. And on Friday, we'll talk about branching flow. We'll talk about what happens if instead of a single pipeline, which have been all the systems we've dealt with so far, series flow, they might change in diameter as you go along them, but what happens if you have flow in parallel? 2 pipes going the same direction, or branching flow, a pipe that branches into 2 parts. And can be relatively straightforward, and we'll talk about flow rate measurements as well. Okay? Thanks very much.